X-rays are light with very short wavelength or very high energy. They have remarkable properties that make them especially useful in scientific studies about the atomic level structure of materials and chemical properties of the elements. In many ways, our modern quantum mechanical understanding of how atoms form into molecules, liquids, and solids is informed by and closely related to studies done with X-rays. Hi, I'm Matt Newville, a Beamline scientist with the Center for Advanced Radiation Sources at the University of Chicago, running an Xray Microprobe beamline at the Advanced Photon Source at Argonne National Lab for Xray absorption and fluorescence spectroscopies. In this video, I'll go over some of the properties of X-rays and how and why they're useful for so many scientific disciplines. This presentation is part of the video series on fundamentals of X-ray absorption fine structure, and also part of the virtual XAFS summer school at the Illinois Institute of Technology and Advanced Photon Source at Argonne National Lab. The aim here is to give some background information on general properties of X-rays so that we can go deeper into details of X-ray absorption spectroscopies in later videos. X-rays are light with very short wavelengths on the order of 0.05 to 50 angstroms, or energies in the 0.25 to 250 kilovolt electron volt range. X-rays are used in many scientific fields for studying the interior structures of materials, the atomic scale structure of materials, the chemical composition of materials, and the chemical state of the elements. You can see here in the visible light, in the electromagnetic spectrum of visible light having wavelengths around 300 nanometers, and X-rays being in the 0.3 to 0.03 nanometer range. X-rays are just light, but they have three sort of separate and remarkable properties, not all unrelated, but remarkable nonetheless. First, they interact weakly with electrons. That is, they can penetrate deeply into matter with a strong contrast in atomic number. This makes them useful for imaging and for tomography methods. X-rays also have energies that are comparable to the binding energies of the core electrons in atoms, and that makes them very useful for spectroscopic studies, which will be the focus of most of this series. And finally, X-rays have a wavelength that's comparable to the distance between atoms in solids or liquids, and that leads to very important properties for scattering and diffraction measurements. In addition, X-rays from synchrotron sources especially have some unique properties that can also be useful and exploited for many applications. X-rays from synchrotrons are highly polarized in the horizontal plane, which can be very useful. It won't be discussed too much in this series, but it is something to keep in mind. In addition, X-rays are highly collimated, and so that it's possible to focus beams at the micron scale or even lower. And X-rays from synchrotrons are partially coherent, that is, being in phase with other X-rays. In this series, we'll focus on the energy property of X-rays, but these other factors can be kept in mind too, as they're very interesting and exploited in many X-ray methods. X-rays are highly penetrating, as I said before, with a strong dependence on X-ray energy and material composition. X-rays are attenuated by matter according to the Beer-Lambert law, which is just the attenuation is exponential in the thickness of the sample, and in some parameter, mu, which we'll call the absorption or attenuation coefficient. I'll go into a little bit of detail on that later. So we have if we consider an incident beam with an intensity of I0 hitting some material with a thickness T, the exiting intensity after the material will be this exponential decay through the material. So this leads immediately to being able to do imaging with X-rays. And in fact, some of the earliest measurements done with X-rays by Röntgen, who discovered X-rays in 1895, here's an X-ray image taken in 1896, and this is very similar to a dental or medical X-ray that you would see even today. The resolution's a little bit worse, but the properties are basically the same. And that is that X-rays penetrate flesh very well, and they are partially stopped by the bone in the hand. And if there's a ring, which will be almost completely metal, the X-rays are almost completely stopped by the metal. And this leads immediately to important uses for medical imaging and for also in research science. And the amazing part of this is that although there are three processes that cause attenuation, there's elastic scattering that can scatter the beam away, and there's Compton or inelastic scattering, and there's the photoelectric effect or X-ray absorption. And for heavy elements, the photoelectric effect or X-ray absorption dominates. And the important thing to know for that is that the photoelectron portion of mu depends linearly on the density of the material, which and then also very strongly on the atomic number, the fourth power of atomic number, and very strongly on energy, the third energy to the third power. So here is the X-ray absorption mu divided by density in over 5 orders of magnitude in mu, and over 2 orders of magnitude in the typical X-ray energy regime for oxygen, iron, silver, and lead. And you can see that on a log scale, even the intensity, the mu value changes dramatically with Z and also dramatically with energy, dropping precipitously with energy. And this is what leads to making it useful for X-ray imaging. You can also see that mu has sharp absorption edges where the absorption coefficient will change by almost an order of magnitude very suddenly. And this happens at the characteristic core energy electron levels for each atom, which are different for each atom. So this property of the photoelectric cross-section going as Z to the fourth power and E cubed is important to keep in mind for every kind of experiment that you do with X-rays. It will inform why at a synchrotron the hutch walls are made of lead, and why you might use some plastic in the beam or some low Z metal like aluminum to partially attenuate the beam, but that you need a heavy absorber like lead to stop all of the beam, and why we can do lots and lots of high energy X-ray work in air because oxygen and nitrogen don't absorb X-rays very much at 10 kilovolts, but at 1 kilovolt or lower, we need to work in special environments where the air is purged. As I mentioned, there are actually three processes that cause attenuation: the Rayleigh scattering, Compton scattering, and photoelectric effect, that all are the way that X-rays interact with materials, with any electron property. For heavy elements, again, the photoelectric effect dominates, but for light elements, especially at high energy, the Compton scattering can dominate. And so while you may have seen in the previous diagram that there was this tailing off for oxygen, that it wasn't strictly linear, although it's pretty linear on a log scale, it's pretty linear in its decay up to about 10 kilovolts. It does plateau out, and that's because Compton scattering or inelastic scattering of the X-rays takes over. You can sort of see this for iron, but it happens at a much higher energy, at more than 100 kiloelectron volts is where those two cross sections meet. You can also see here that the Rayleigh scattering, which is the elastic scattering, as we'll see, that will give rise to scattering useful for diffraction, is considerably lower than the absorption cross section, almost over the entire range we have plotted here. And again, these sharp edges are characteristic of the core levels. So the photoelectric effect, that is the dominant process for how X-rays interact with matter, was described by Albert Einstein and was what he was awarded the Nobel Prize for. In this effect, an X-ray enters or is absorbed by an atom by kicking out one of the deepest core level electrons, perhaps the tightest bound or the 1s or k shell electron. The X-ray energy goes to that electron level, which is kicked out into the conduction band. If there's any, this leaves the atom in an excited state with a core level hole, an empty electronic level, and any excess energy of the core level electron is given to a photoelectron that is ejected from that atom. That's the photoelectric effect, leaving the X-ray is absorbed, completely destroyed, and the photoelectron may be released with excess energy given from the binding level energy for the deep core electron. When that atom is in the excited state, it will relax. And that relaxation of the excited state gives rise to Xray fluorescence, which is a very important companion process to Xray absorption. So with an atom in an excited state, you can have a higher energy electron drop into that core level, and that will emit an X-ray or light that is characteristic of the difference in those energy levels. So the 2p level dropping to a 1s gives so-called K alpha emission, whereas a 3p electron dropping down to the 1s emits K beta X-rays. And this discovery or this understanding really led to an important understanding of how electrons are arranged in atoms, and led to a rearrangement of the periodic table based on atomic number instead of atomic weight, and so on. And really remarkable phase change in how we understand atomic properties of the elements. In addition, though, in addition to being able to kick out another fluorescent X-ray, an electron can also be emitted. To do that, an electron from the 2p level will drop down to the 1s level, and an electron from the 2p level will also be promoted out of the atom into the continuum, and that will also preserve momentum as well as energy. And this is the Auger effect, described first by Lise Meitner, who, among all the people here, is the only one who did not receive a Nobel Prize for that discovery. So these are very important for having discrete energies that are characteristic of the absorbing atoms. And means that they can be very useful for identifying atoms. So you can shine X-rays on a material, look at the light that comes off. The X-rays that come off are characteristic of those elements, and then be able to tell what the composition of the material is. And so that leads to Xray fluorescence spectroscopy, where fluorescent X-rays at characteristic energies from different elements can be used to identify and even quantify the elemental abundances, often down to ppm levels. So in modern electron probes and Xray Microprobe beamlines, Xray fluorescence spectra can be collected so fast that they can be made into elemental maps of elements of the elements within a few hours. So here's a map of a 10 by 9 millimeter map with 5 micron resolution collected, showing potassium, manganese, and zinc all separate in a hyperaccumulating plant grown in 2 different conditions. And these spectra here resolve and are very easy to use to identify what elements and what abundances are available or are in material. And in addition, right at those core levels, we have Xray absorption spectroscopy, which will be the focus of much of the discussion in this series. And Xray absorption spectroscopy is the modulation of the Xray absorption coefficient, that mu value, at energies just above that core level excitation. So right when we can now promote the 1s electron out of, for here, an iron atom, then we get these oscillations and features in that Xray absorption coefficient that give us XAFS or XAS, the Xray absorption fine structure spectroscopy, or the Xray near edge spectroscopy, or the extended XAFS. And these contain information about the chemical state and local atomic environment of the atom. We'll go over this in much more detail later. The main characteristics for XAFS is that it's sensitive to the local atomic coordination. It's sensitive to the valence or an oxidation state. It can apply to any element, and it works at fairly low concentrations, down to ppm or micromolar. There aren't very many sample requirements. It's an atomic level spectroscopy, so you don't need pure or even pure crystals or crystals at all. And or specific isotopes to do the analysis. It works on effectively any element with Z greater than about 3 or 4, 2 or 3. In fact, if we look at the near edge structure for a few candidate atoms, we can see that it's very sensitive to the chemical state and formal valence of the absorbing element. So here's chromium, 2 oxidation states, chromium 3+, chromium 6+, and their Zane's spectra are remarkably different. Similarly for arsenic 3 and 5 are easy to tell apart. And then for, and this is true for, these are only examples, this is true essentially for all oxidation states for almost every element. For iron, here are some spectra that show iron metal, and iron 2+, and 3+, and something in between for magnetite. And you can see that the oxidation state can easily be determined from XAFS spectra. And that's to say that this is really probing what are the unoccupied electronic states that photoelectron that's kicked out in the absorption, in the photoelectric process, what electronic states can that photoelectron fill? Again, we'll go into much more detail about this in later videos. And far above the edge, these oscillations in mu consist, and these are sensitive to the positions and types of atoms in neighboring atoms. We'll define the XAFS oscillations as mu of E, and we'll see these oscillations going out several hundred electron volts and be able to use that to get local atomic structure from the elements. Finally, for the properties of X-rays, I want to talk about using the X-ray wavelength and X-ray scattering and diffraction. Again, the spacing between atoms in most molecules and solids and even liquids is typically in the 1 to 10 angstrom range, often actually tighter than that. And X-rays have the right wavelength to scatter. That's Rayleigh or elastic scattering. So again, one of the lower probability scattering or interactions with X-rays, but still important. And so these X-rays can scatter elastically from planes of atoms in a solid. And when they scatter elastically, that is, they lose no energy at all, they can scatter in phase with either their self or the next X-ray over, and then that allows constructive interference in the scattering. And when X-rays are just at the right angle and scatter from X-rays constructively to interfere, they can diffract. So a very strong intensity can go at a very particular angle of scattering. And this can tell you then the spacing and the arrangement of atoms in a crystal. So you can get out the crystal structure very easily into very high precisions. And to be clear, diffraction is although it's one of the weaker interactions, it's the most common use of synchrotron X-rays. And even for lab X-rays, it's very common to use laboratory X-rays for X-ray diffraction measurements because this ability is so to determine the atomic structures of materials is so strong. These days it's done at very high speeds, but basically when the X-rays are at the right wavelengths and angle of incidence to a crystal, they can diffract according to Bragg's law. These are the two Braggs, father and son, and also Max von Laue, who won Nobel Prize for describing this work well. And here are the Bragg's law is a very simple description of when diffraction will happen. That is when the wavelength is times some integer is 2 times the spacing between atoms, d, and the sine of the angle. Then you get very strong peaks. So you'll end up with a diffraction pattern. Many of you have probably seen diffraction patterns like this. That can be assigned as the different lattice planes. Here's a diffraction pattern for iron carbide. And this has been remarkably successful in describing the atomic structures of materials. Of course, these days, something as simple as iron carbide doesn't need a synchrotron radiation or even much work in a lab, but even over the last 50 years, working on much larger molecular systems, including proteins or samples at extreme conditions, is common. So these days, X-ray diffraction and synchrotrons involve either very large molecules or portions of very large macromolecules. Samples at extreme conditions on very disordered materials like liquids or surfaces or buried interfaces. It can also be done at very high speed to see the dynamics of crystals changing in real time. And it can be done at very small scales at high precision to measure strain, for example. So here are common modern X-ray diffraction patterns and the structures that can be solved with them. Really remarkable methods for that. So let's talk a little bit about how X-rays are generated and how we use synchrotrons to generate light and why that's important for our studies. So light is generated by accelerating a charge. So if you accelerate a charge at low energy, with low energy electrons, you get low energy light. So a radio tower, for example, has an AC current that produces radio waves, which is light in the regime of a meter or so. X-rays have wavelengths that are at 10 to the minus 10 meters or so. So something like 10 orders of magnitude different. You can also generate X-rays. So you can generate X-rays by slamming electrons, say from a cathode ray tube, into a metal. And this is how an X-ray tube that might be in your lab or your dentist office works. Electrons are generated and put through a magnetic field to accelerate them and then slam into a metal target, copper, tungsten, or so on. And then the X-rays are produced both from the fluorescence of the X-rays, so you get out discrete levels from those X-ray emission lines of the metal that emits, and from the deceleration of the electrons, so you get a broader spectrum of X-rays from that deceleration. In a synchrotron, we accelerate high energy electrons by turning them in a magnetic field, and this gives very high fluxes. So here we have a ring, and we'll start with very high energy electrons. So at the APS, we use 7 or soon 6 GeV X-rays. That's 14,000 times the rest mass of electrons. So these are highly relativistic. And then you got to keep the electrons going around the large ring for many hours. So you need an RF, a radio frequency cavity to put energy back into the electrons. As they go around, they're going to emit X-rays, and that's losing energy. So you got to make sure that they stay at the right energy. That's what the radio frequency cavity does. And then X-rays come off at tangents at every time the X-rays are accelerated or bent. So a bending magnet, here shown in red around here, every time the X-rays bend through a bending magnet, X-rays will come off at the tangent. And that gives a beam line, so we can take those X-rays and use them downstream. Down here we can put our X-ray equipment and do some material science or some environmental science with that bending magnet radiation. In addition, in between the bending magnets, in the sections that are straight and so-called straight sections, you can insert devices. These are called insertion devices, and that would be an alternating pole, so north-south, north-south, north-south. So the electron beam will turn one way and then the other way and then the other way and take many turns, maybe even 50 or more turns in a single straight section. That gives many more turns, which gives much higher fluxes of X-rays, both higher flux and brighter. I won't go into the difference between wigglers and undulators here. Maybe that'll happen in another video, or you can look that up separately. So a synchrotron or storage ring is a ring with many of these beamlines. It'll have many bending magnets and probably many insertion device beamlines in between them. And all those beamlines that produce X-rays can run simultaneously. The electrons go around in an orbit several 100,000 times a second probably. And so each one of these beamlines will get X-rays continuously. So in the US, the Department of Energy runs 4 synchrotrons as user facilities, and there are many more around the world. And the brilliance or the flux of monochromatic X-rays in a highly collimated beam, that's brilliance, is very high in synchrotrons. So synchrotrons have very high flux and highly collimated. So compared to the sources that are the X-ray tube sources from copper, molybdenum, or Bremsstrahlung down here, the brightness from bending magnets or undulators and wigglers from, say, the APS or ALS or other beamlines run by the Department of Energy are many orders of magnitude higher in brightness and brilliance. So modern synchrotrons are large. They have circumferences that are on the order of a kilometer, and they have dozens of beamlines each. So the APS, the Advanced Photon Source at Argonne National Lab, has about 60 simultaneous independent X-ray beamlines running continuously, and each one is doing a different scientific experiment. So at the APS and at all synchrotrons, there'll be some bending magnet lines and some undulator lines, the high brightness lines, and the APS runs 200 days a year. Beam time per year, when it runs, it's 24 hours a day, and somewhere between 25 and 90% of the beam time at each of the beam lines goes to a peer review process, peer review proposal. So it's open to the scientific public for access for science based on the proposal. So each of these beam lines will have a series of lead enclosures or hutches that hold the X-ray optics, monochrometers, mirrors, and slits, and so on. And then in any experimental equipment that protect, and these lead enclosed rooms protect the people from the radiation, again, because lead, being high Z, absorbs all the X-rays. The experiments will happen something at like 40 meters from the source or more at the APS, maybe 40 to 60 meters. And most of these 60 or so beamlines are dedicated to a single or a handful of techniques or a scientific discipline. And most of the beamlines at the APS are run run by A&L, but some are run by outside groups. But all of them are open for at least some public access from peer review. So I think for this portion for this talk, I think we've shown you that X-rays, especially from synchrotrons, are extremely useful for many scientific disciplines. They're used all the time, continuously in biology, chemistry, geology, physics, archaeology, material science, energy science, environmental science, basically any kind of science you can think of that needs to understand the structures or the chemistry of materials. And that's because they interact weakly with electrons, so they penetrate deeply. And they have energies that are comparable to the binding energies, so spectroscopy can be done on the elements, core level spectroscopy of atoms. And then the wavelengths allow us to do these amazing diffraction and scattering experiments. If there's one thing I'd like you to remember going forward about the X-ray properties of materials, it's that mu is strongly dependent on Z and strongly dependent on energy. As you do more X-ray absorption and other work, this fact is important to keep in mind almost all the time in any experiment design or thinking about how the experiments are actually working. And finally, more information on X-rays and X-ray absorption spectroscopy especially are available at some of these resources. There's a review article, a website, a couple of books, which are either specifically on XAFS. Both of these are excellent books by Grant Bunker and by Scott Calvin. And then this book, Elements of Modern X-ray Physics by Al Nilsson and McMorrow, is a wonderful book on all sorts of X-ray physics. So thanks, and if you have any questions or comments, you can leave them in the comment section below or let me know in the context of this course. Thanks for paying attention. Thanks.